In this section, we're going to talk about what's called the binomial probability distribution. Now, unlike the previous section in this chapter where we discussed expected value and we had outcomes and their associated probabilities, in this particular case, we're talking about only two possible outcomes. So things like acceptable versus defective, survive or died, success or failure. And in order for us to be able to answer any type of questions about our binomial probability distribution, we first have to verify that it is in fact a binomial probability distribution or a binomial probability experiment. And we can verify that by making sure that our experiment meets all four of these requirements you see on the screen. The first requirement says that our experiment must be performed a fixed number of times. Now, each repetition of our experiment is what we call a trial. So we have to understand how many times we're going to repeat this process. The second part of this experiment that must be met is that each of our trials are independent. Remember when we talked about probability, two terms were considered independent of each other if the probability of one event does not impact the probability of another event. And that's what we're referring to here. The third requirement that must be met in order to be a binomial experiment are that each of the trials are mutually exclusive, have two mutually exclusive outcomes. Again, back in probability, we talked about that term mutually exclusive. It meant that you could not have any overlap. The outcomes were not overlapping, implying that they were then mutually exclusive of each other. They were disjoint was another way that we framed it. So what we're saying here is that each of our trials has to have two outcomes. In this case, we refer to them generally as success and failure. And finally, the fourth requirement to be met in order to have a binomial probability distribution is that the probability of success, however it's defined in your problem, is fixed for each trial. So it's not going to change from one trial to the next. So all four of those requirements have to be met before you can go on and do any type of analysis using this binomial probability distribution. So because of that, let's look at an example here and let's determine whether each of these examples meet the binomial distribution criteria. So the first example says that we are rolling 5 dice and we need to get at least two sixes, to win the game. So I have 5 dice. I'm going to roll the 5 dice, and if 2 of those dice have 6s on them, I win the game. Now the first requirement of the 4 that were listed above is that our experiment has a fixed number of trials. So if we're looking at this, I would ask you, how many times do we get to play the game? Well, if you're reading that sentence right there, it's not really stated how many times we get to attempt to roll the 5 dice to get the 2 sixes. So because we aren't told how many times we get to play the game in order to achieve the 2 sixes from the 5 dice, this is not a fixed set of trials, and therefore it is not a binomial distribution. Okay, remember that rolling the 5 dice is considered one trial or one experiment. Let's look at the second one here. We record the eye colors found in a group of 500 people. The first part of this binomial experiment says that we have to have a fixed number of trials, and if you look at what the sentence says, we're going to talk to 500 people, so that would be our trials. Previously, we've said that that's the sample set, so our sample size is 500. The second criteria are that each trial is independent. So we're checking for independence. Now my question here is, if I look at the eye color of one person, does that impact the eye color of another person? Hopefully you can see that that is not the case, so we would say that these probabilities would be independent of each other. The third criteria are that there are two outcomes, two mutually exclusive outcomes, as a matter of fact. If you look at the sentence, we record the eye colors found in a group of 500 people. Well, there are 4 or 5, depending on how you count it, eye colors. So there are not two outcomes. So therefore, this is not a binomial distribution. Now, if I had said I wanted to record the eye color, I wanted to record the color of brown eyes in a group of 500 people, then that would be two outcomes, because you would either have brown eyes or you wouldn't. So that's where the two outcomes would come from. But in this particular case, we haven't defined a particular eye color we're looking for, so there's not two outcomes. The next one you see here says a manufacturer recalls a doll because about 3% have buttons that are not properly attached. Customers return 37 of these dolls to the local toy store. Is the manufacturer likely to find any dangerous buttons? So dangerous buttons meaning that they're not properly attached. Remember, the first criteria says that there has to be a fixed number of trials. And so if you see here, the number of trials is our sample size of 37 dolls. The second criteria is that they are independent. And we would say that the likelihood of one doll having a not properly attached button versus another one not having a properly attached button is independent of each other. So yes, they're independent. Number 3, are there two outcomes? Yes, there are two outcomes. The two outcomes would be, is the doll defective or not? And then number 4, what is the probability of a defected doll? Or in this case, with the sentence that you see there, the probability or the percent of dolls who have buttons that are not properly attached is 3%. So the probability of defective is 0.03. So I'm going to change all my percents into decimals from here on out. So all 4 of these requirements have been met. This is the only example we've looked at so far where our example is in fact meeting the criteria for a binomial distribution. So this is the only one so far. Okay, the next example. A city council of 11 Republicans and 8 Democrats picks a committee of 4 at random. What is the probability that they choose a Democrat? So again, fixed number of trials, yes. They are choosing a sample size of 4. Are they independent? Ask yourself, if I choose one person, the probability that I choose a Democrat of one person is not necessarily impacting the probability of another. So I would say yes, they are independent. It's a pretty small sample size, so we're just going to leave that one as it is. Let's talk about two outcomes. What are the two outcomes that we're interested in here? We're interested either in a Democrat or not a Democrat in this particular case. And then the fourth is the probability the same for each of my events? The answer to that is actually no. Now, let's think about this for just a moment. We have 19 total names we're going to put in a hat, let's say, because there's 19 possible choices up here. So if I put 19 names in a hat, the probability that I pick a Democrat, so the probability I draw a Democrat out of the hat on the first try are 8 total Democrats out of 19 people. So 8 out of 19. The second time I draw, so for the second Democrat, there's one less Democrat, so that would be 7 Democrats to choose from, possibly, and I have 18 people now to choose. So I could have drawn a Democrat the first try, but I would have one less the second try. I would also have one less person total in my sample space. So if you notice, the denominator here is changing each and every time, which means when I draw a name the first time, the probability changes now to the second time that I draw, because I've reduced the number of total options there in the hat. So because we could not meet all 4 of the criteria, we would say this is not a binomial distribution, and it was that last one, that the probability is not the same for each trial, that threw it out. Okay, and finally, let's look at this one here. A 2002 Rutgers University study found that 74% of high school students have cheated at least once on a test. Your local high school principal conducts a survey in homerooms and gets responses that admit to cheating from 322 of the 481 students. So, first criteria says, are there a fixed number of trials? And you can look here and see, yes, the trials would be 481 students, or the sample size ends up being 481 students. Are they independent? Yes, the probability of one student cheating does not impact the probability of another student cheating, in theory. Another thing I would probably say is that, generally speaking, when you have people you're talking about, so like this, we're talking about a survey of people, or any type of polling or something like that, we assume that people are independent of each other, that they have their own choice that they can choose. So we can say, yep, I've got people here. Sure enough, we've got independence. Number 3 is talking about 2 outcomes. Yes, there are 2 outcomes here, whether you cheated or not. So cheat or not. And then 4th, what's the probability of cheating? So the probability of cheating is, according to this study, 74% or 0.74. So because we have been able to meet all 4 criteria, this is only the second one of our 5 examples that did meet the binomial distribution criteria.